We're on. All right, today is polymerization again, polymerization 2. So we're looking at polymerization. All right, and this one we're looking at the other type, condensation. Okay, so this is condensation polymerization. Michelle wants to come in. Why do I have to physically allow people in? Why don't they just automatically join, I wonder? Is it always like this? Oh, that's weird. Anyway, so we're looking at condensation polymerization. Now, before we have a look at this, we have to look at a very specific reaction called esterification. Okay, and obviously, as the name suggests, it's forming an ester. Now, an ester is an organic molecule that has this functional group. Okay, this is the ester functional group. This thing here. Okay, if you see that, the thing is an ester. Esters are quite weird things, actually. They're very perfumed. They give us lots of the lovely smells we smell around. And they also give, Misha wants to come now, they also give taste as well. So we eat a lot of esters, whether you like it or not. So they give taste to our food as well. So they smell and they have lovely taste. I don't think anyone eats them anymore, but they used to be very popular. These banana chappies. Do we eat any chappies anymore? All right, and the banana ones were full of an ester called ethyl ethanoate. Okay. Anyway, that's a tiny bit on esters. But how do we form an ester? An ester is formed when a carboxylic acid reacts with an alcohol. Okay, and when a carboxylic acid reacts with an alcohol, we get an ester and water. Okay, now this type of reaction, when two molecules come together to form quite a big molecule and a small molecule splits off, this one splits off. This type of reaction is known as a condensation reaction. Okay. All right. So carboxylic acid and an alcohol will give us an ester and water. You should know this. I'm sure you do. We use concentrated sulfuric acid as the catalyst, and we use heat as well. And they're the conditions to make an ester. An ester smells good. Okay, so I'm going to give an example of an ester, how we make an ester. The carboxylic acid I'm going to use, we always use ethanoic acid, so let me use a different one. I'm going to use propanoic acid. So 1, 2, 3 is propanoic acid. I'm going to react the propanoic acid with, now we always use ethanol, don't we? So I'm going to use something else. I'm going to use methanol. There's methanol. So on the left, we've got my carboxylic acid. Whoops, what's going on there? Carboxylic acid. And on the right, I've got my alcohol. Now, the carboxylic acid that I've chosen here, that's a nice green. This is propanoic acid. Propanoic acid. And my alcohol, the one I've chosen, is methanol. Okay. Now, what happens then when these two join together? Let's have a look. Where's my thing? Now, when these two join together, believe it or not, the OH from the carboxylic acid and the H from the alcohol, this splits off, and this is going to form my water. Okay, and how do we generate the rest of the molecule? Well, we just add these two bits together. So this is going to give CH3. You should be able to do this, actually. It's a very good skill. So CO. Now the next thing, all of the water's gone. So the next thing, let me do it a different colour so you see what I mean. Let's do it in this colour. Is the oxygen from the methanol. And what's given off? What's split off? Well, we have an OH from the carboxylic acid And what colour do I use this one? And the H from the water, and that's the water. That's what splits off. And this new thing, as you can see, we've created this functional group I mentioned up here, and this new thing is an ester. Okay. Now, before I go on, I'm going to have a drink. All right, I've got my nice chilled drink here. Are we all okay? I never ask you guys. I should do. I know. I should ask you more because otherwise it's just a video. Oh, Zara's yee. She likes Kanye. All right, all good. Has anyone learned anything? Be honest. Be honest. Because I don't know where to pitch these things. Tiso, are you just being nice or are you being honest? Zara's being honest. All right, Zara, thank you for your honesty. I'll move on then, shall I? Oh, well done, Mother Butter. Mother Butter's being nice. But Zara, I appreciate it. No, but that's good. Very nice. All right, now, Zara, then, since you're such a genii at chemistry, what's the ester called? What's the name of this guy? What's the name of the ester? Oh, I see. All right. Anyone know the name of it? Right, the name of esters. I'll carry on talking now because we don't want to be up all night doing this. The name of the ester. Well, there's two names to an ester. There's a first name and a second name. The first name always comes from the alcohol used. Let's have a look. Something 8. Well done. Well done, Mabato. You're right. The first name comes from the alcohol, and the second name comes from the acid we use. Now, the alcohol we used is methanol, so the first name becomes methyl. The second name, where we use propanoic acid, so the second name is propanoate. So Mabata's quite right. It's known as methyl propanoate. Okay. Now, everything looks good here. All right, we have a carboxylic acid and an alcohol that come together. Water splits off. Now, as I've said, I'm pretty sure, yeah, this type of reaction is known as a condensation type reaction. There we are, condensation reaction. And what's the definition of a condensation reaction? It's when two large molecules come together and a small, let me change that, and a small molecule splits off. Okay, and there's the small molecule that splits off. Now, it's called a condensation type reaction because the water molecule that splits off is often in the gaseous form. It bubbles out, and it used to condense on the side of the test tube. So they call them condensation reactions. It doesn't have to be water, but on our syllabus, it's always water. All right, I know other condensation reactions. Sometimes you get HCl, that's the small molecules. Sometimes you get ammonia. Sometimes you get urea. You get all sorts of small molecules. Okay, but in our course for Form 5, IGCSE, the only molecule that splits off is always water. All right. So are we all okay with this concept of esterification? By the way, this is a condensation reaction and then often known as esterifications because we create an ester. Okay, so this is an esterification reaction, and all esterification reactions are condensation type. Okay, they're condensation. So everyone's good before we go on to polymers, because we have to start here. Oh, well done, Misha. You answered quickly. Zara's good. So Teng's good. Excellent. Right, let's move on then. Now, so I've obviously used the word condensation. All right, so condensation polymerization must be something to do with this, what we're doing. So now we're going to look at condensation polymerization. Polymerization. All right. Now, what we had before, we had an alcohol, okay, and we had an acid, okay, and what we had before, and I'm going to do the proper one. 1, 2, 3, 4, 5, 6, OH. And the acid, believe it or not, is 6 as well. 1, 2, 3, 4, 1, 2, 3, 4, 5, 6. We had an acid and an alcohol. up there. If you reacted these two together, okay, let's have a look. I'm drawing these, and while I'm drawing these, because hydrogens take forever, while I'm drawing these, anyone want to give me the name of this ester? The ester that would form if these two molecules reacted. Anyone want to tell me? If this acid and this alcohol reacted together, what would the name of the ester be? Oh, crying out loud, so you're quick. Yeah, I think it is that, isn't it? Unless I'm mistaken. The acid is hexanoic acid. Hexanoic acid. And the alcohol is hexanol. And so it would be called hexyl hexanoate. Well done. Exactly right. Okay. Now, what would hexyl hexanoate look like? Well, it would have 6, 1, 2, 3, 4, 5, 6, and then 1, 2, 3, 4, 5, 6. It would look so. I'm not going to put all the hydrogens on this thing, but it would look something like this. And it wouldn't be a polymer, though, would it? It would be a bigger molecule. It would. Oops, it does it in this share mill. Right, here we are. Okay, welcome, Nissim. Right, now, it wouldn't be a polymer though, would it? It would be quite long. This guy's quite long. It has 12 carbon atoms, but it's not a polymer. So if I react these two together, I don't get a polymer. I just get a very big ester. So we have to modify our starting materials. Does anyone know what we have to do to our starting materials to create a polymer? Now, the reason I say that because I want to give myself a little bit of time to get rid of all of this rubbish. Get rid of that. So now know what I have to do. How do I modify my starting materials? Not quite, Zara. All right. Anyone know? I'll show you. If you don't know, that's fine. It's no problem if you don't know. All right. To make them react so they form a long chain, I have to have. Now watch this. I'm going to rub things out. I'm going to rub this out here, and I'm going to rub this out here. To make them form a chain, I have to have a functional group at either end of the molecule, so they can grow from the left and from the right. If I've only got one functional group, two only will come together. But if I have functional groups on the left and the right, they can grow from both sides and form a polymer. Does that make sense? Anyone? Does it make sense? Zara, that's okay. Right. Okay, that's good. I'm glad you said that. Yeah, you're right, Melissa. You're right about that. But Zara, I think it will become clear, so not to worry. If I have two functional groups, it can grow from both sides. If I only have one functional group, it can only grow from one side. Okay, Zara, a good explanation I use is this. There's a person. All right, he's got two hands. And there's a person. And this person has two hands as well. Okay, let's chop off one of their arms. It's a bit cruel, but it's got to be done. Name of science. Let's chop off this arm. Okay, now if I ask these two one-armed people to hold hands, how many people will I get in my new molecule? Zara specifically. If I ask these to hold each other's hands, how big would the molecule get? How many people? Yeah, two. Oh, very good. Two people, yeah. So they would join hands here, wouldn't they? Okay, and I'd get two. Two people. But, let's get rid of these guys. And this is, I hope you're all getting my analogy here. But now, I've got two people with two hands. Now, they can join hands here. But another person can join hands here. And another person can join hands here. Yes? So how many people, if they've got two arms or two hands, how many long will this get? Zara. Zara. Long. It will get long. Okay? Now, if I have 100 people, you can get 100 people. You get 10 people, you can get 100 people, you can get 1,000 people. I remember they did this in England once to see how long they could get. I think they managed to go pretty well from the left to the right of England, holding hands. All right, it was a really big project, but they did it. And there was a time when literally they were holding hands across the country. It took about 100,000 people or something. Anyway, but because they've got two hands, they can grow from either side. And if they can grow from either side, the molecule or the polymer can get very, very long. Does that make sense? Anyone else? I think Zara's gone off for a cup of tea. Hold on, let's have a look. All right, Zara, no, but as long as you understand roughly what I'm saying, okay, I'll get to that question in a minute. Can we all see Zara's question, by the way? What's the science? We're going to get to the science in a minute. So, can we all see Zara's questions, or is it just me? Oh, there's something weird's happened there. All right, doesn't matter. All right, no one wants to talk to me today. All right, including my wife. But anyway, that's another story. Right. So now we have functional groups at either end. Okay. Oh, we can see it. Well done, Michelle. You can see functional groups at either end. Now, this, if it has only one functional group, it's called an alcohol, isn't it? But believe it or not, if it's got two functional groups, the same functional group at either end, we call this thing here, this alcohol, it's got two because it's called, and now it would, if it had one functional group, it would be called hexanol. Okay, hexanol. But it's got two functional groups, and Mabato came up with a lovely idea. It's now called hexane 1,6 diol. All right, and the reason it's called hexane 1,6 diol is because there's an alcohol group on number 1 and there's an alcohol group on number 6. And we call it a diol now. So in other words, diol means there's two ols. Okay. Now, similarly, and that just means there's two functional groups, one at number 1 and one at number 6. This one down the bottom, well, if there was only one functional group, this would be called hexanoic acid. But this is called hexane 1,6 dioic acid. And that just means it's got a functional group at number 1 and a functional group at number 6. So this is known as hexane 1,6 dioic acid. Now, as you've seen me struggling horribly with writing all of these H's everywhere, an acceptable abbreviation for this is this. Okay, instead of drawing this hexane 1,6 diol, I can put all of this stuff in a box. All of this stuff is here, but I can rewrite this as this. Okay? And this Cambridge allows before anyone asks. All right, this is totally allowed. Now, for the 1,6 dioic acid, it will look like this. And I can draw a box. Let me draw the box here. All right, and I'm going to draw a box here. There. It just simplifies the molecule, doesn't it? Makes it easier to draw. All right. Now, how many carbons are in here? In the top box? Anyone? How many carbons in the top box? Well done, there's 6. How many carbons in the bottom box? Yeah, oh no, my butter, there's only 4 in the bottom. Because there's one outside and there's one outside this side. Okay. Now, because the boxes, one contains 4 and one contains 6, we should differentiate the boxes. In other words, we can't have a box because a box should mean the same thing. So what we do is we tend to shade one. Okay, just to show it's not the same as the other box. They're different boxes. So now what we're going to do is we're going to draw what would happen in a chemical reaction. So now I'm going to use different colors now because I want to. We have the OH here. We have the box. And there is my dioic acid, dicarboxylic acid. And I'm going to draw another one here. And I'm going to draw another one here. I think that's about all I can fit in. There we are. there's another one here. So hopefully this will answer Zara's question. Now, I did say we should shade them, so I'm going to shade these ones. And now in between, what colour will I going to pick here? Let's pick this lovely green. I'm going to do my alcohol. And there's the box. And this represents my hexane 1,6 diol. All right. Now, obviously, there'll be one here as well. Okay, and there's going to be one here since I've got space. Why not? Okay, and now I'm going to put these under pressure and do some spooky stuff. Heat them up, put them under pressure and temperature, and they're going to bash into each other. And I'm going to get a wonderful reaction called polymerization will happen. Now, watch where I draw my loopy loops. This OH, remember we did it before? It's going to come apart. This OH and this H. This H and this OH. This OH and this H. This H and this OH. This OH and this H. There you go. And when these two groups come together, obviously water is going to split off. There's one there. Another one there. H2O. Another one's going to split off here. And another one's going to split off here. So let's rewrite the polymer now. All right, so now it's going to look something like this, isn't it? It's going to be O, box, O, and then it's going to be CO, O, shade, O, and then it's going to be O, box, O, and then it's going to be CO. Now I'm going to stop after this one. No, all right, I'll go on. I quite enjoy these. Whoops, that should be an O, shouldn't it? No, it doesn't matter. O, and then C, O. And then, well, it's got to end somewhere. So if you were here on Monday, you'll know what this is. These things are known as my continuation lines. I must draw these. Yeah? And what we have now is the reaction reversible. It is, yes, we can reverse this. I'll tell you in a minute. No, do I want to? Yeah. In your body, I don't know if you know this. I'm sure you do know this. If you do biology, you should know this. But in your body, we store energy in very similar molecules like this. We store energy in esters, okay? Now, in esters, another way of saying esters, crazy but true, is fats. So the fats in our body are, believe it or not, they're esters. They're not quite similar to these, but they're very similar. Sorry, what am I trying to say here? They're esters, but they're not quite the same as this. They're tiny bit. Oh, Amusa is coming. They're a tiny bit more complicated than these. All right, a tiny bit more, but they're fats. So, Zara, if you do biology, if you metabolize a fat, what do you get in biology? Just tell me what you get in biology. Anyone can answer. If you metabolize a fat, what do you get if you metabolize fats? Fatty acids and glycerol. Yes. Now, fatty acids are carboxylic acids. Yes. Which are these. Yes. And glycerol, believe it or not, is just a very fancy alcohol. It is cool. I agree. Science is cool. So, and we get that. These are the alcohols. So when you metabolize fats, you get carboxylic acids and glycerol, which in chemistry we would call carboxylic acids and alcohols. And it's all the same thing. It's beautiful, isn't it? It is cool. So at least we've learned something today, all of us. All right. So let's get rid of that. Well, I didn't learn it. I knew it. Right. So, oopsie daisy. Let's move this up. And there we have this new thing. Now, don't forget, when it formed, what came out, every time there was one of these groups here, water formed as well. So the water split off, didn't it? I know I've drawn it above, but let me do it again. So What type of reaction was that formed this polymer? This guy is now our polymer. These guys are our monomers. Okay, so what type of reaction caused this polymer? Well, water split off all the way, so it's known as a condensation type reaction. And so this type of reaction is known as a condensation polymerization. Okay, so that's where we get condensation polymerization from. Now, what does this particular condensation polymerization form? It forms an ester. Let me get a different color. All right, there's the nice color. And if you look here, what's this group? Anyone know what that group is? Have we seen that group before? Oh, Zara. Bloody hell. Here we go. You didn't answer my previous question, to be fair. I don't think I phrased it right. What I was trying to ask is how would we get the functional group to attract both ends of one monomer? E.g., how would we attach the OH to both ends of the alcohol? Well, if you've got alcohol groups, yeah, they will be naturally. Yeah, I know what in real life means. The alcohol groups from the alcohols, okay, these are naturally attracted to carboxylic groups. Okay, so just naturally, what's going to happen is one molecule. There's an OH and there's an OH. This is just floating around, all right? And it will eventually, one side will react with a carboxylic acid, and you'll get this unit. Okay, something like that. And then maybe another carboxylic acid will come along and it add to the other side. Okay, and basically it would grow from both sides. Yes. Now, I don't know if you've done this in biology, but the reason the OH groups and the carboxylic acid groups are attracted to each other is something called hydrogen bonding, which you may have heard of in biology. They're attracted to each other because of hydrogen bonding. Okay, so if you have a bunch of diols and a bunch of dicarboxylic acids, dioic acids, if you have a bag of diols and if you have a bag of dioics, all right, and you shake them together, they will form a polymer. All right, and why is that? Well, because naturally the OH groups are attracted to the carboxylic acid groups. How do you make the? Is that all you wanted? How did the alcohol become a diol? Oh, guys! Oh gosh! Anyway, you sausages. If that's it, how do you make a diol? All right. Gosh. I'm gonna say stuff that you might not like here. All right. How do you make a diol? All right. So I'm trying to think how I'd make one. Right. From crude oil, let's start from crude oil. We get this stuff. All right, this is called ethene, as you know. All right, this is called ethene. Okay, now if you react ethene with an oxidizing agent called potassium manganate, all right, it will put an OH on either side of the carbon of the double bond. So I've made a diol there. Okay. There's many ways we can make diols. This is a very basic way that I've done it here. But basically, you create a double bond in the molecule. You wouldn't know how to do this. That's why I'm not going into too much detail here. But you create double bonds in molecules, and then once you've created a double bond, then you can oxidize the double bonds. And once the bonds have been oxidized, they put OHs on either side of a double bond. Okay, it's known as mild oxidative addition. Okay, is that good enough, Zara, for now? It's a. Is this addition reaction system? Yeah, exactly. Oh, yes, it is. Oh, Zara, very posh. Yeah, it is. But that's way above us at the moment. All right, it's an interesting reaction. Chemistry is interesting. I think you guys, you guys give it a bad time, but it is a very, very interesting subject. Seriously. All right. Maybe we don't teach it right, but it is a very interesting subject. Anyway, So Zara's kept quiet, I hope. Right, now, as I was saying, what do we call this functional group here? What's this functional group? This is an easy one because we've seen this functional group before. I'm not even going to ask you. This is known as an ester, isn't it? Yeah. It is an ester linkage. Oh, yeah, let's talk about that for a minute. You're quite right, though. These in the polymer are known as the units. There's a unit, and this is a unit. These are called diunits. Now, this unit, as you said before, contains 6 carbons. This unit contains 4 carbons, and this unit contains 6 carbons, doesn't it? What holds the units together, as Zara just said, are things called linkages or links. So this is a link, and this is a link. What is the type of the link? It is, again, as Zara said, it is an ester link. Yeah? And because there's many ester links, yeah, the polymer is therefore known as a polyester. Okay? Are we good with that? So polyester is a condensation polymer. Everyone okay with that? That this is called a polyester? Yeah? I hope we're okay. Are we okay? All right, good stuff. Well, thanks, I think. Now, if you can't vary the links. Any polyester will have ester links. Okay, they're normal. All right, but you can change the units. You can change the units from 6 carbons. Maybe you want 4 carbons, or you can put some weird things in these units. You can put these benzene ring things. You don't have to know what they are, but if you change the units, you change the polyester. So there's not one polyester, there's literally hundreds and thousands of polyesters. And how do we get different ones? Well, we get different ones by changing the units. But we don't change the links, we only change the units. Now, the one on our course, all right, the particular polyester on our course is known as Terraline. Okay, Terraline is a fancy name. It doesn't give you any idea of the structure, does it? It's just the name of the molecule. And you'll often see it with a little C there because it's a copyrighted name. Okay, but it's just a name. All right. So in our course, polymers, polyesters are Terraline. And what do we use Terraline for? Well, we use them mainly for clothing. All right, they're used for clothing. Now, if you look at your shirts, most of your shirts, okay, if you have a cotton shirt, all right, let's pretend you've got a cotton shirt, and these are the fibers of your cotton shirts, okay? Cotton shirts are lovely. We all love cotton shirts. Pure cotton shirt. This is a pure cotton shirt. Now, I don't know if you know this, but if you wash your cotton shirts, the cotton, because it's got strands everywhere, all right, what happens is these strands get tangled with each other, okay? So in your lovely cotton shirt, the strands get tangled, and once you've washed it, all right, sad but true, the strands are really pulled closer together because these strands tangle and knot and stuff. And so you start off with a lovely big shirt, you go and wash it, and the shirt comes out of the washing machine and it has shrunk. Okay? So what we do as chemists, well, we all love cotton. Okay, so we're going to keep our cotton shirt, but in between the strands of cotton, we put strands of terraline. And these terraline strands prevent the cotton from tangling up with each other. So if you look at your shirt, I can't remember the percentages. A cotton shirt, a pure cotton shirt, is obviously 100% cotton. But if you look at your white shirts, the ones most of us have these, it will be cotton, I don't know, 65%, and it will be polyester. What's the other one? 35%. And the polyester that it will be terraline. Okay, are we cool about that? Is everyone good? So one use of terraline is for clothing. Excellent, thanks, Anna. It is cool. You know what? Chemistry is cool. It really is. Honestly, I'm not joking. Right, so that's Terraline. Let's have a look at another one. Now, there's two to go, so I better shut up and get on with it. All right. Now, the other one is nylon. This is our other condensation polymer. Okay, this is a condensation polymer as well. Okay, but obviously it doesn't have ester groups between it. It's going to have what we call amide groups. Okay, so it's going to have amide linkages, not ester linkages. Okay, so let's have a look at our monomers. Now we have a diacid as we did before. Okay, and I'm going to represent the diacid like this. There's my diacids. Okay, and that's just like the one before. And the other one is a 1, 2, 6 seems a good number for these, by the way. All right, this thing has an NH2 group on either side. Okay, why did I draw this? All right, and we get this. And if you're interested in chemistry, I've forgotten how to name this. I'll give it a shot in a minute. Okay. This is a diamine. Okay, this functional group is known as an amine. Okay, and there's another amine group there. There's two amine groups. Now, what's it called? I'm going to guess 1,6-diamino hexane. I'm guessing. I think it's called that. I can't remember. All right. But anyway, so for nylon, we have a diacid and a diamine. Now, Cambridge are nice again. Whoops, let's get that one. Cambridge are nice again, and we can chop this out. And this. No, we don't really. You just don't worry about it. I think it's not too hard, though, Zara, to know about this. But no, you'll see what you've got to learn when you look at the past papers, I think. Yeah. So don't worry too much. Just enjoy the chemistry for now. That's all you got to do. So we can represent our diamine like this. Okay. All right. There's my diamine, and I've got to shade it. All right. So there you go. We have a diacid and a diamine. Now we're going to do this quick. All right. So what did I draw first? Let me do my diacid first. There's my diacids. I think you all know what I'm going to do. There's my second diacid. Let's try and do 3. Oh, 4. What the hell? All right. You know what? I should cut and paste these, shouldn't I? I keep forgetting. There's my diacid, my diacids, my diacids, my diacids, and my diacid. And in between these, I'm going to squeeze in my diamines. Now I'm going to do this in a different color. I'm going to say, oh, this is a bit messed up. All right, so NH2. Ooh, there's a tiny box. I've tried to squash too much, but hopefully it won't make much difference. You'll understand what's going on. There's NH2, NH2, and NH2. All right. Oh, what a mess. All right. Ugh, that's horrible, isn't it? Now, these should be shaded, even though they're tiny. But you know what I mean. They're the thing I drew up there. All right. Same thing's going to happen. You're going to get a condensation reaction. And the OH from the carboxylic acid and the H from the amine is going to come off. It's going to happen here. It's going to happen here. It's going to happen here. Ugh. It's going to happen here. It's going to happen here, obviously, but I haven't drawn that one. And it's going to happen here, and I haven't drawn that one. So, what we're going to get, well, the magic of chemistry, we're going to get polymerization when these two stick together. And it's going to look like this, isn't it? It's going to be this, and then NH. And then the box, and then NH. And then CO, and then the box, and CO, and then NH, and then the box, and then the NH, and then the CO. All right, and then the CO continuation line, and then the CO continuation line. All right, and then we're going to bracket it off to show it goes on forever. And as you all know, let's do this color. Every time there's one of these links, we get a water. There's water there, water there, water splits off. Water splits off. So, what type of reaction caused this? Well, it was a polymerization. And what type of polymerization? Well, it was a condensation polymerization again. So this is the second time. All right. Now, what's the difference? Well, we've still got our units. This is a unit there, and there's another unit there. Units look pretty much the same, but the linkage is different now. Okay. This is a new linkage. Okay. Now you've got to learn that linkage, CO and H, and this linkage is known as an amide linkage. Okay, an amide linkage. Now, the amide linkage, there it is. All right, that's the amide linkage. These are our monomers. And down here, this is our polymer. Okay, so what I've drawn here, the polymer, must be, well, as the other one was called a polyester because of the linkages, this is known as a polyamide. Okay, and the polyamide, interestingly, all right, in here, how many carbons are in here? There's 4 carbons in here, and there's another carbon there, another carbon there. So from this bit, we get 6 carbons. In here, if you remember, there's 6 carbons as well, and there's 6 carbons here, 4 in there, and 1 there, and 1 there. So there's 6 here, and there's 6 in here. So crazy but true. This polyamide that I have drawn there, if it's 6 and 6 and 6, is known as nylon 6,6. Okay, because the monomers that made it had 6 carbons in. So nylon is just a fancy name, and therefore it's copyrighted as well. And we use nylon for things like plastic bowls. Now the washing up bowls we use, plastic bowls, ropes that we use on our cars to keep things down, stockings, yeah. They're very thin stockings that women wear. There was an interesting story about that because the guy that developed nylon and made stockings he was outed for his homosexuality during the 40s and 50s, and he actually killed himself. All right, it's a character called Carruthers. I can't. If I could spell it, it would be good, wouldn't it? Carruthers. You can look that up if you want. But he was an interesting chemist that killed himself. Anyway, so that's nylon. So we've got 2 types of condensation polymer. We have polyesters and polyamides. Polyesters give us what do polyesters give us? Terraline, and polyamides give us nylon. Okay, so they're there, and both of these are synthetic. So far we've only done synthetic ones. We've done if you remember from the other day, all addition polymers, every one of them, all of them are synthetic. Okay, now condensation polymers, so far we've done synthetic ones, but we're going to do one now that's not synthetic. Now the synthetic condensation ones are Terraline, which is a polyester, and nylon, which is a polyamide. Okay, so, last one. Okay, and this is going to be a condensation reaction as well. So we're looking at last one, one last condensation polymer, but this one is going to be natural. Okay, now I like these ones best. All right, so these ones have an NH2 at one end, and then they've got a box, and then they've got a acid group on the other end. Okay, and I'm going to draw a different color. We have an NH2 group on one end, and a box, and an acid group. Well done, Misha. Well done indeed. We have an NH2 group on one end, and a box, and a carboxylic acid end on the other one. Now these guys are going to be our monomers. These are our monomers. And you can see they've got two functional groups. They've got an NH2 functional group and a C double bond O functional group. Now, does anyone know what these molecules are called? What are these molecules known as? What's their name? If you don't know, say, I don't know. Someone will know. Well done, Misha. They're amino acids. Why are they called amino acids? Let's have a look. Well, because as I said before, one end is the amino group and this other end is the acid group. So that's why they're called amino acids, because they have amino groups or the amine groups and the acid groups. So these monomers are called amino acids. Okay, and all amino acids have an NH2, and all amino acids have a COOH. The only difference between one amino acid and the other is the funky bit in the middle. Okay, we don't call it a funky bit in the middle, by the way, in chemistry. Believe it or not, we call it something called an R group. We call this in chemistry and biology. This is known as the R group. I don't know. Have you heard of that in biology? The R group? Anyone? Okay, but that's for next year if you do science, I guess. Right. Oh gosh. Now, when these guys, what do? They condense. Now, how do they condense? Exactly like we've done it before. The OH from the acid, and the H from the amine. The OH from the acid, the H from the amine, the OH from the acid, and the H from the amine. All right. So let's draw it out where we have NH box COO. Then we've got this color that I've just got rid of. NH box and oh, sorry, that's wrong. Oh, what's going on? Right, there we are. Then we have the CO, and then I'm trying to keep the colors consistent. NH box NH continuation. Don't forget your continuation lines. So there are my continuation lines. And there we have, when amino acids come together, they form the polymer. And as Misha has quite rightly said, polymers like this are known as proteins. Okay, they're proteins. Now, as they come together, as again, you get an H2O given off and an H2O given off. And this direction here is obviously known as condensation polymerization. Okay. Now, and we get amino acids out of them. We start off with amino acids and we get proteins. Let me color them in because we should make it nice. Has that got that? This got dots for some reason. Why on earth I did that? And this one got this thing, lines there. All right, so this is a protein. Now, if you look closely, you can see, yeah, this is the last one, dear. I know we're all tired, aren't we? Right, so there we've got our unit. Can anyone see what that unit is? Well, we've seen this unit before, haven't we? It's an amide unit. Yeah, that's the link, isn't it? So proteins are polyamides, just like night pink, the link. Have I got messed something up? Is the last one right? Oh, I see. I thought you meant is it the last one we're doing? No, you're right. I've messed that up, haven't I? Well done. Well spotted. It's where we need people like you, dear. All right. There you go. But I think you knew what I was getting at, so it's not important, is it? So there you go. And we've still got to do the concept, but well spotted. Shows you're awake, dear. More than I am. All right. So proteins are called polyamides. All right. But why are they called polyamides? Because the linkages are amides. Now, interesting question. Does anyone know what we call these links? In chemistry, we call these links amide links. Does anyone know what we call these links in biology? Anyone? The CONH? Anyone? Oh, no one. I think everyone's gone to sleep. What do we call in chemistry? We call them amino, and I want you all. Well done. They're called peptides. All right. So I want you all in chemistry, though. I'm not being funny. You've got to call them amides, eh? You can't call them peptides. There is a reason. I'm not going into why, but you've got to call them. But these links are known as peptides. This is a peptide linkage. Okay. It's not really a peptide. Oh, you sausage, Zara. They're called peptide linkages. Do you not do it in biology? It's not called a peptide. It's never called a peptide, dear. So it's a peptide because it's a special type of linkage. All right. Does this not come up in biology? Peptides? No one? Okay. All right. So in chemistry, we call these polyamides, but in biology, they'll often use the term polypeptide. Okay, for the same thing. All right. But we don't. We call it amide. We don't call it a polypeptide. We could do, but we don't. All right. Now, Zara's asking me why it's called a peptide. To be honest with you, I don't know. You know what? In the old days, dear, when chemistry and biology they used to be so far apart that literally similar things would be called different things. So chemists would call them amides, and biologists would call them peptides. All right. But these days, when biology and chemistry are getting so close together, these days, it's unreal. In fact, I'm sure you know that there's a Nobel Prize for physics, there's a Nobel Prize for chemistry, but there's no Nobel Prize for biology. But the people that win the Nobel Prizes for chemistry these days are often research biologists. All right, because the subjects have come so close to each other, which is a good thing. All right, it really is. Right. Anyway, guys, so these are the ones. Okay. Now, the very, very, very last thing we'll do, because it's getting late now, if you break up a protein, well, you get back to being amino acids. Okay. Now, we do this in the body. Okay. And if a biologist asks the same question, how do you chew up a protein to get the amino acids? They would say, well, it's digestion. Yeah, and enzymes do the digesting, don't they? They break up the proteins back into amino acids. But in chemistry, we're not as clever as these enzymes. What we do is we heat them up with hydrochloric acids and aqueous and heat them. Okay, and we break them up, and the proteins break up into the amino acids. But in chemistry, does anyone know what we call this process in chemistry? In biology, you call it digestion, but in chemistry, we call it something else. Anyone want to guess? Anyone? No? All right. What do we have to add to my protein to make amino acids? Well, when the amino acids made the protein, what molecule came out? Water came out. Does that make sense? When we did the condensation polymerization, water came out. So going the other way, water must go back in. Yes? Well, not quite hydration, dear. It's quite close. So water goes back in, and when it goes back, well done, it is, even though that's not spelt correctly, yes. But water goes back in and it splits up the molecule. So because it's water, we call it hydro. Okay? So the reverse reaction is known as hydro for water. All right? And the Latin for splitting up is known as lysis. So we call the reverse reaction where you have the proteins back into the amino acids, we call it hydrolysis. All right? Because it's splitting up using water. That's what hydrolysis means. Okay. Anyway, guys, you've been wonderful and you've been very patient because it's 10 o'clock. My God. Apologize to your parents for me, please.